In section 3, we're going to discuss the nomenclature of organic molecules. In other words, how to name organic molecules. So there are two types of chemical names that you are likely to encounter. The first one are called common names. Common names are generally the older names of chemical substances. However, many are still used today for common substances, especially industrial substances, typically smaller than about 5 carbons. So these days we mostly use what's called the IUPAC system. The IUPAC system is periodically updated, and we're going to see some consequences of that when we do naming. But these are generally considered the official names of chemical substances. So one of the goals of the IUPAC system was that it would be systematic. In other words, it would have a system of rules, and furthermore, they wanted all compounds, all substances to have a unique name so that you wouldn't accidentally grab one substance instead of the other based on a name. And finally, they wanted the name to be based on the structure of the molecule, of the compound, so that you could look at the structure and you would know what it was called. So if we look at an IUPAC name of an organic substance, we see that it basically has 5 parts. The 5 parts are listed here in these boxes. We start with the stereochemistry, then any substituents, which are branches attached, then a main parent chain, which we will talk about, any unsaturations, and then finally the most important functional group. Putting these pieces together, we come up with an overall name for the molecule. Now, I have created a stepwise procedure to constructing these names as follows below. You can see this. First, we're going to identify what we call the main functional group and any unsaturations. We are then going to identify and name the parent chain using priority rules. We're going to number the parent chain using numbering rules. We will then name and number the unsaturations and add those names after the initial parent chain name. We will then name and number the main functional group and add it after the unsaturations. We will then name and number all the substituents and put those in front of the parent name, and finally we will do the stereochemistry and add that in front of the substituent. The first skill we need to have then is to identify what we call the main functional group and any unsaturation. Now, we are not going to do this for all of the functional groups this semester. Instead, what I've done is I've selected the functional groups that we are most likely to encounter in first semester. So that list is shown here. And what we see is that the functional groups have a priority to them, starting from highest priority down to lowest priority. In a later chapter, we'll talk about how that priority is roughly determined. But the important thing is that when we have a molecule that has 2 or more different functional groups, only one can be the main functional group, and the other functional groups we will see later will be treated as substituents. So here they are. These are actually, should hopefully be familiar to you from our earlier discussions of functional groups. But this semester we're going to learn how to name carboxylic acids, aldehydes, ketones, and alcohols. And their priority order is carboxylic acid is the highest, then aldehydes, then ketones, then alcohols. Now, alkanes, alkenes, and alkynes are functional groups, but we are going to treat them as unsaturations. And in fact, we need to identify all of the unsaturations. A molecule will have only one main functional group. We will choose the highest priority functional group from the table above, but then we will use all of the unsaturations. It should be noted also that halogens and ethers, which are technically treated as functional groups, technically we call functional groups, they are not named as functional groups. Instead, we're going to name those as substituents, and we will discuss that later. Once we have identified our main functional group and any unsaturations, we then look at the structure of the molecule, and what we want to do is identify the longest carbon chain that contains the main functional group and unsaturations. So I have some examples here to show you sort of some of the subtleties of this. The parent chain that we identify, the longest carbon chain, that has to contain the main functional group, and it needs to contain as many of the unsaturation as possible. Now, if there's a conflict because, for example, there's a branch and one unsaturation is in one chain and a different unsaturation is in another chain, or the functional group is in a different chain, the priority order is this. The functional group has first priority. It must contain the main functional group. Then double bonds, and then triple bonds. Okay, so let's look at our examples. So in this example, in this first example, what I've done is I have already numbered the two possible chains. So for example, starting here, we could go 1, 2, 3, 4, 5. That would be a 5-carbon chain. If we look at the green numbers, starting here, we could go 1, 2, 3, 4. So just looking at it, it might appear that the red numbered chain, 1 through 5, should be the main parent chain. But if we look, that chain does not contain this double bond unsaturation. It does contain the carbon of the main functional group, which would be the alcohol. So if we chose this chain that I have circled in blue as our parent chain, that would be incorrect. The longer chain has the main functional group, but it doesn't have the double bond in it. So going over here, this is the same molecule. The correct selection would be this one with the green numbers. Choosing this one that starts with the alcohol functional group and continues down past the double bond to the end. So even though this chain is longer, because it doesn't contain the double bond, it would not be the main chain, the parent chain. Finally then, I have a very, very similar example. You can see that again we have 1, 2, 3, 4, 5, 6 bonds, carbons in this chain right here. Here is our main functional group, so we could either use this chain or that chain potentially because they both contain the functional group. But what we saw is double bonds have a higher priority than triple bonds, so we're going to prefer the chain that has the double bond, which is the one that I've circled in blue. So you can see, using these rules, we should be able to pick out a parent chain, and I highly recommend that you circle that chain so that you can see which chain you're working with, so that you can see more clearly which carbons you need to count, etc., etc., etc. Once we have identified our parent chain, then we need to count the number of carbons in that chain, and then we need to give it a name. Now, the parent chain name is based on the number of carbons in the chain. The parent chain names for 1 to 10 atoms or carbons is given below in this table, and you should memorize this table. This is something that you're going to be expected to know even when you go on into other classes that use organic chemistry or even on standardized exams. I'm going to focus on this first column right here. These technically are the names of the parent chains, leaving out the unsaturations or the functional group. So you can see that 1 is meth, 2 is eth, 3 is propa, buta, penta, and so forth. The first 4 names are probably derived from common names that existed before the IUPAC system. But after that, you can see that basically the 5, 6, 7, these are based on Greek or Roman prefixes that indicate these numbers. So pent, hex, hept, oct. These are probably prefixes that you've heard before in other contexts. The other thing is that you can see, starting with 3 carbons, these names end in A. The 1 and 2 do not. And we will often drop the A when we get to adding the names of the unsaturations. Okay? So the rule is, for parent chains that end in A, the A would be dropped when the next part of that A starts with a vowel. Okay, now, there are some other issues that come up when we're trying to select a longest carbon chain. For these examples, I'm going to use just alkanes, which have no functional group in them. They have no main functional group, and they have no unsaturations to sort of change the way we would select. So we're really just looking for the longest continuous chain of carbons. So the first issue is that the longest carbon chain can be written bent and curled up and twisted. It may not necessarily be the longest straight horizontal line as the structure is drawn. So this would be an example of that. If we look at this structure, we have on a horizontal line this chain. 1, 2, 3, 4, 5, 6 going to there. So that would be a 6 carbon chain. But if we look carefully, there is another chain that starts at 1, 2, 3, 4, 5, and then branches and goes down out of the horizontal to 6, 7, and then 8. So since that chain would be longer, we would select that as our parent chain. And I've circled it out in blue. Similarly, we run into problems when the chains fork. So what I've done here is I have a line structure of a molecule, and I have sort of highlighted a red chain and a green chain with numbers. So if we look, the red chain has 7 carbons in it. The green chain, which comes up to carbon 5 and then branches down here, also has 7 carbons in it. So now we have the problem that we have 2 possible longest carbon chains. In that case, we have a rule. We select the chain that has the most branches. So if you look, this chain here, once we go to this fork, there actually are no branches attached to that fork. In contrast, if we go to the green fork, we come down on the chain, and then we have this CH3 group branching off. So we are going to choose, in this case, the green chain as our parent chain. Once we've identified the parent chain, we need to number that chain so that we can say where other groups are located on that chain. So the number, the location of a substituent or a functional group or a substituent, a functional group or an unsaturation is called the locant of that substituent. That's the number on the chain. Now, numbering will always start from one or the other end of a chain. So that means there's always 2 ways to number a parent chain. In other words, starting from either end. So we will need to have rules for selecting which end will be number 1. And here's the rules. We start numbering from the end of the chain that will put all of these different groups at the lowest numbers possible. So for example, our main functional group takes the highest priority. We definitely want to get that at the lowest number possible. Then if we have a choice, or if there is no main functional group, we want to put the first carbon of a double bond at the lowest number possible, then a triple bond if there is no double bond or if we have a choice, And finally, when we have just single substituents or substituents without functional groups, without double bonds, we want to put those at lowest numbers. And I'm going to show you an example of how that would work. Okay, so here are a couple of examples of carbon chains, parent chains, that we would want to number. So let's start with this one. So what I've done is I have put one numbering system above in red and a second numbering system below in green. Now, this carbon chain has a main functional group, which happens to be this alcohol. And so main functional group has priority for the lowest number. So if we compare the red numbering system, in the red numbering system, that main functional group would be at carbon 5, whereas in the green numbering system, that would be at number 2. Well, 2 is lower than 5, so we would choose the green numbering system for this molecule. Going over here, this is a molecule that has no main functional group. So in that case, again, I have a red numbering system above, a green numbering system below. We have a substituent and we have a double bond. But when we look on our chart, I'm going to slide up a little bit, we can see the double bond has a higher priority than substituents. So therefore, we're going to try to put the double bond at the lowest numbers. In that case then, putting the double bond starting at number 1 instead of having it start at number 4 would be preferred, so we are going to choose the red numbering system. Coming down here, again, we have no main functional group, but what we have is a double bond and a triple bond. So now, in the red numbering system, the double bond starts at number 2 and the triple bond starts at number 4. In the green numbering system, the triple bond starts at number 1 and the double bond starts at number 3. If we look, double bond has a higher priority for numbering. So therefore, we would choose the red numbering system, where the double bond has the number 2, as opposed to the green numbering system, where the double bond has the number 3. Finally then, I have an example where I just have a single substituent. In that case, again, we have the red numbering system, the green numbering system. The red numbering system would put the substituent at carbon 4. The green numbering would put it at 2. Since 2 is lower than 4, we would choose the green numbering system. So you can see, you have to work it out, but the rules are fairly straightforward and they're very systematic. One situation that we can encounter is when there are multiple substituents, but there are no functional groups or unsaturations. Remember that functional groups and unsaturations are going to take a priority. These substituent groups will not inherently have a priority. So what we do in that case is we actually pick the two numbering systems. So I have the red numbering system on top, I have the green numbering system on the bottom. Now what I've done is I've circled the substituent groups, which in this case are all CH3s, but they could really be many different carbon groups, they can be halogens, they can be ether groups, and there is no priority among them. They're all just treated as substituents. In that case then, what we're going to do is we're just going to basically list the locant numbers for the substituents in each numbering system. So for example, in the red numbering system, I have a substituent at carbon 2, at carbon 5, and at carbon 6. So 2, 5, and 6. In the green numbering system, I have a substituent at carbon 2, at carbon 3, and at carbon 6. So 2, 3, 6. I list them in increasing order so that I can match up equivalent locants. Then what we're going to do is we're going to read through and find the first pair of locants between the two systems that are different. So for example, 2 and 2 are identical, but 5 and 3 are different. That's the first one that's different. So that is what we are going to use to make our choice. I generally line these up on top of each other and then circle the two that line up that are different. And then we just compare which number is lower. In this case, the green 3 is lower than the red 5, so therefore we would choose the green numbering system. And so then that would be the correct numbering system. There are a couple other considerations for numbering. For example, be careful, numbering does not always necessarily start on the left. So here's an example. You can see this molecule. Here would be, these 4 carbons would be our parent chain, and our substituent is right here. We want to number from the right to put that substituent at carbon 2, as opposed to numbering from the left, which would put it at number 3. This is just sort of an artifact of the fact that we're accustomed to reading from left to right, and so we have a natural tendency to want to start numbering on the left. But again, depending on how the molecule is written, that may not be the correct numbering system.